And in this panel, we will be finding solutions to the major problems that we have. We have a constant production, we have a variable demand, and it is the storage in between which acts as a buffer. Today, in this panel, I have panelists who will be telling you about economical and best ways of storing the products. We have some innovative chemicals also coming over there. So now first of all, I am requesting my first speaker, and before I do that, I will request the speakers to be on time. There is a timer over there. Normally at the start of the meeting, I ask people to switch off their noise making devices, but I think there is so much noise all over the place, it's not required. So, but please try not to disturb the speakers, because they have made so much efforts, research in preparing their speeches. So if you want to go out or move, please do so during the applause, not while the speaker is speaking. So with that, I am requesting my first speaker, Dr. Altaf Usmani. Please, he is DGM Technical in Engineers India Limited, and he will be talking about large-scale underground storage of LPG in rock caverns. Mr. Usmani.
Good afternoon, everyone. Okay, so as with the permission of the chair, as sir rightly said, as part of this theme, I will be covering the very first part on the underground storage problems. So I think some of you must be knowing around Engineers India Limited has been working on finding solutions for the storage of different kind of hydrocarbons beneath the surface. We have the available options of storage right now, where we can see in terms of the surface storage. But what we are looking beyond something, the surface storage, beneath the underground storages, where our dual purpose can be solved. And I will just take you through in next 15 minutes how we are doing this process. So starting with a very brief background, I think that was the tone of the conference yesterday, that coming to the fossil fuels, we are moving slowly towards the LPG, which is a more cleaner fuel assumed, and the growing demand of the LPG in both rural and urban areas. So that's why, with respect to the crude oil, now we are getting more inquiries about the LPG storage. And very soon we are moving into the natural gas storage also, because these are the two new hydrocarbons coming up. So now coming to the requirement, why an underground storage is required? Why not we just satisfy ourselves with the surface storage only? Now there are a lot of challenges what we can go through, starting from the geological subsurface options. We are looking, the basic philosophy why we want to go underground is that we are looking something, a very large amount of storage, a very safe storage from external threat, a kind of a storage which can work in all around the weather conditions, irrespective of type of climate, where we can take the product at any level, and we can utilize the land for other reasons, because in a country like India or every place, the land cost is very important. So we are looking for the solutions where a dual usage of the land can be done. So this is one of the success we recently got. That also I will share you how a land can be utilized in both the ways. Now coming to some of the basic concepts. So this is the first one, which you see all around the refineries areas, the steel tanks. So we are using it for storing different kind of purposes, but the major issues with them are a lot of external attacks, high land cost, and also the limited capacity in terms of the volume that we can store. Now then comes the options of the underground storage, what we can do. So the next three options what you see, these are the options where right now as EL we are working for finding out the solutions. The first one being the buried concrete tanks. the second one being the unlined rock caverns, and third being the salt caverns. So these are the three working options we are working, that how we can transfer the storage requirements by going deep and deep underground for mass storage requirements. So as you can see, the major benefit what we have from a surface storage, it's like a deep cover, a high security, a dual uses of land, and a very important one, a mass storage option. So these benefits add up, that why we need to go underground in terms of the storage requirements, that normally we are not having when you are doing a surface storage. Now I will come back to, with a limited time, I will try to solve, present with you. So this is the first one, the unlined rock caverns. So what is the principle? As you can see, there is a product inside a rock cavity and there is a water pressure outside. So the simple principle we call it as hydraulic confinement, where the outside water pressure is always more than the product pressure. So you are confining the product within the rock, deep inside 200 meters, 300 meters inside, and there will be no leakage because the outside water will always have a more pressure than the internal pressure. So this principle we call as hydraulic confinement. Now this just to show a typical layout, just to have a better understanding of this. So you can see the bottommost part, the brown part is the storage area, all others are the tunnels. And in that also you can see the blue tunnels. So these are the water tunnels which create the required pressure from outside. When I was talking the pressure, this is the pressure of the water through these tunnels, which will be higher than the cavern storage area. So you will have an external pressure from the water, which will be always more than the product pressure. Whatever you are trying to store, either it can be crude oil, it could be LPG, and in future it can be any kind of other gas. Now coming to what we have so far developed in India. So in India we are moving ahead quite a fast pace, and this is the what you can see in our country, the biggest underground rock cavern ever built in India. You can see the amount of the dimensions right from the 10-story high building, 30-meter high and 20-meter wide, and another cavern that's for crude oil, and we have recently completed another project which is the largest LPG storage cavern, which is around 80,000 metric ton. So these are the two projects we have done for the crude oil. Crude oil basically we have done 3 projects, and LPG we are on the verge of completion 1 projects. So these gives us an advantage that how we can solve the problems of storing mass levels without any kind of external and internal threats. So briefly I will put up you some challenges what we see and how we overcome. This was the project located on the Mangalore region, and I think if you must be aware, this is a very climate challenges in terms of heavy rainfall. So we have tried to overcome these challenges with some very innovative design techniques what we have used in terms of the stabilization of the soil, the slopes, because in order to enter the tunnel we need to have the slopes also. Similarly, the best part of this project, the term I was using, the dual usage of the land. Now here comes the challenge. The LPG project recently completed was completed in a running plant facility. So that makes it even more challenging and interesting for us. But we successfully completed this project. So you can see the live existing plants at the surface, and beneath 100-150 meters you have all the tunnels and cabin located, which gives you a perfect dual usage of the land. But for this, definitely when you are doing something new, new challenges are also there, because we are doing a drill and blast. So once you are doing a blasting, you have to take lot of precautions also. So we did lot of new things. We envisaged new design techniques so that the blasting damage can be reduced, and how we can work under an existing project. So that was the key concept successfully used for the LPG storage project. Coming to the another challenge, as I told you, these are quite deep projects, so the only accessibility we have, because once the project is complete, you won't be able to enter inside. There is no maintenance, nobody can go inside. It's a one-time project. The only accessibility we have is the shaft. The shaft is something which is connected from the surface and which goes deep inside 200 meter where the actual LPG storage project is located. Now this shaft itself has a lot of challenges, because we start with the soil, depending upon the soil conditions, and then we go deep inside the rock. So what you can see, the two figures, we start with the soil part, and then we go deep inside, 200 meter inside, and this is the shaft where all casings and pumps are located for taking the product inside and outside. So this is the key component of the storage project. Here also we use lot of innovative techniques to do it in minimum time, and especially the weather conditions. And the most important part is the equipment selection, because we are working in a confined diameter of 7 meter only. So you have to select your product, your design, your engineering based on the type of dimension you have in hand, and also the cost and the schedule. Now, in addition to what we do in engineering, we are also having, these projects are underground, and you have lot of uncertainty associated with this. So you have a live monitoring systems running for all, right from the geotechnical monitoring, the hydrogeological monitoring, the vibrational monitoring is a key parameter, which is basically the blasting requirements. So all these monitorings make an important role in these projects, because underground storage projects, the observation is very important once you are going deep and deep. Now, as part of this underground management, we have also devised a system, especially for the underground, which we call a risk management methodology. Once you are inside, there are a lot of risk, and you have to be thinking beyond to develop all the risks. What could you encounter? What could be the challenges? Who could be the owner? And what will be the remedial measures? So you have to be a bit ready with all these if you want to do the project in successful execution period. Now coming to some of the experience EIL has developed so far in terms of these projects. So right now we have done almost 10 kilometers for rock cavings. You can imagine a 20 meter wide, 30 meter high, 10 kilometers of long cavings we have made for storage of crude oil and LPG. Then we have also done a vertical shaft, which I just showed you, almost 170 meter deep, is having from 6.5 to 8.5 meter dia. We are doing, as part of these projects, a lot of slope stabilization. We are doing a lot of monitoring, and the most important part, we are doing a risk management plan. So a successful project must have a good risk management plan so that you can take up the challenges at the right time. Now coming up some of the key points what we have observed. In these projects, because the ground is the main, ground can be your enemy, ground can be your friend. So we are developing some kind of principles that how to go ahead with these projects, so where the client and contractor both can have some better idea in terms of what could be the geotechnical reference conditions. We have special manpower deployment. Normally in most of the projects, you don't see the blasting expert, the risk expert, and the data monitoring expert. So these are the key positions developed out of these projects in addition to other positions. Same way, as I told you, the most important part is the dual usage of the land. And lastly, whatever the muck or the rock we are using, we are getting from the excavation, we are using it for different purposes. So that is an additional benefit of the rocks excavated. Lastly, we at EIL are working on a new concept, which in the future you are going to find out, for a different kind of gases which need higher pressure, which I should say kind of a natural gas or something. So we are developing a technology to store gases, because remember, crude oil, it's a very simple 1.5 to 2 bar. LPG you are storing at 8 to 10 bar. But for other gases, like for natural gas, you want to store as a compressed form, you need 100 to 200 bars. So very soon we are developing a technology where you can store high pressurized gases also beneath, external, safe, and a mass storage option. Just to have an appreciation of what we have done, I will show you a brief video for your better understanding.
Energy security is pivotal to India's growing ambitions. Global crude oil price volatility and supply disruptions necessitate robust strategic measures. Recognizing this, the Government of India envisioned a strategic petroleum reserve program to safeguard the nation against energy contingencies. EIL has played a pivotal role in this initiative since its inception, overseeing the conceptualization, design, and execution of India's strategic crude oil reserves. Under Phase 1, EIL successfully delivered underground rock cavern storage projects at Visakhapatnam, Mangaluru, and Padur, with a combined capacity of 5 million metric tons. Underground unlined rock caverns are an advanced and proven storage solution. This technology employs groundwater pressure to securely contain hydrocarbons. Each facility features interconnected caverns, vertical shafts, and sloping floors that ensure efficient oil flow and vapor pressure control. The design is rooted in meticulous geological investigations, ensuring both stability and safety. In addition to crude oil storage, EIL has achieved a landmark feat with India's largest LPG storage facility in Mangalore. This 80,000 MT rock cavern project exemplifies EIL's engineering excellence, navigating complex challenges and enhancing energy storage capacity. Looking ahead, EIL is expanding its expertise to align with India's integrated energy policy. From Phase 2, crude oil reserves, to pioneering new designs for pressurized hydrogen and natural gas storage, EIL continues to innovate for a sustainable future. With accolades like the National Geoscience Award and groundbreaking contributions to underground storage technologies, Engineers India Limited is not just building energy infrastructure. It is building resilience, sustainability, and a brighter tomorrow for over 1 billion people.
Thank you. That's all from my side, and you are always welcome to visit our stall. Thank you. Thanks a lot. I hope I am on time.
Very well on time. Mr. Usmani, thank you for this comprehensive review of this technology where rock caverns can be used for LPG storage. I think the next session, next panelist is also on the same subject, and for the strategic requirements, all the countries, they need their energy security, and for that India is also developing its own strategic storages, and we would like to request Mr. Ajay Dashore. He is Chief General Manager Production from Oil and Natural Gas Corporation Limited. So his company is already drilling oil for us. So now they are helping us with storage also. So Mr. Dashore will be talking about the strategic crude oil reserves. Please, Dashore.
So, first of all, I would like to thank Dr. Altaf for giving a presentation on this. EIL has been our partners before. For last 7 years, I was with Indian Strategic Petroleum Reserves, and now I am back with ONGC. But by the time this was done, I had been with this. So, the topic here which I would be dealing is strategic crude oil reserves, which is a viable alternative for creating oil storage capacities. So right now our refineries etc. have facing issues for the building of above ground tank capacities etc. So how can this be used as an alternative to above ground tank capacities? So I would be focusing, and how does this concept of strategic reserves came to India? So the evolution was started. This was started during 1998. During the government took cognizance of the shortage of crude oils. So first time when there was a crude oil supply disruption, that was in 1973 during Arab-Israel war. At that time, the OPEC organizations put on a embargo on exporting of crude oil, and at the same time then US government decided to build their own caverns that were salt caverns. So the basic concept started from that time to counter the shortage of global price hike and to take care in case there is a supply chain disruptions from the Arab countries. So first was the US which created those reserves, and then our other countries followed on. So India also decided to go on for this crude oil storage caverns. So this were primarily to be used during supply side disruptions and shortages, to provide economic and national security during any energy crisis or emergency situation. So suppose a war breaks out, and during that period your all supplies to the refinery is curtailed. So how do you work out? During that time your reserves are there from which at least your refineries can, you can supply the crude oil to your refineries, and then you can continue with war, because those are the most essential period. So right now we have almost 10 days with strategic crude oil reserves, where we can supply oil to all the refineries, plus the refineries have their own above ground tank capacities. So with that, total capacity comes around 74 days, which we can sustain for the during the war period or energy crisis. So this also adheres to the principle of PM's four pillars of energy vision, that is energy security, energy access, energy efficiency, and energy sustainability. So as Altaf had said, we have built in a total capacity of 5.33 million metric ton, which is almost 39 million barrels of crude oil at 3 locations, which is Visakhapatnam, Mangalore, and Padur. These all facilities took almost 6 years to be constructed from start. Like we started in 2011, and last one was commissioned in 2018 in Padur, which is near Udupi. And that one at the Padur is the largest one. At one single place, you have a storage of 2.5 MMT, which is almost 20 million barrels of crude oil. So now you must be aware there is a IEA, International Energy Agency. So this was created in 1974 to coordinate with the major oil disruptions. So there are 31 countries which are members of that, and 13 associate countries. India is an associate member of this IEA since March 2017. So to become a member, there is a condition that you should have at least 90 days of the previous year's net imports, which a country has to maintain, and to which government can have immediate access and can be used to address the disruptions during the supply. So India at present, as I said, we have around 74 days, and in phase 2 we are going to construct another 6.5 million metric tons capacity, which is almost 50 million barrels. In that, so we'll be getting around 84 days plus additional tank storage capacities. So we hope to reach for 90 days. Presently, that's why we are at a stage of associate membership. The member countries can maintain these stocks mainly in industry stocks or public stocks held by the government. So this is one of the pictures of the cavern gallery, which was taken during the construction period in 2013. This is almost 700 meters long, and this is a 0.625 MMT storage capacity of Padur. As you can see on the side, it's totally unlined. There's no lining of concrete or steel. And in this tunnel, you will have a crude oil storage, which we are having storage done into this. So the question here is, since it is unlined, what will happen if there will be crude oil storage? There would be vapors in the space. So that vapors would go through the fissures in the caverns or unlined rock space. And so how do we counter that? That is by the principle of geological confinement. So water seeps inside these caverns through the water curtains, which Dr. Altaf had shown in the slide. It keeps which maintains a positive hydrostatic pressure, and the water gets collected into the bottom at the cavern, and that is again recirculated through water lift pumps, and then treated and again recycled. So I'll show you one covering in the process how it is done in this. So this is a typical cross section of the main cavern. Here the height of the cavern is almost equivalent to the 10-storied building, and you can see while construction it's a 30-meter height. So you do the top heading, then bench 1, bench 2, bench 3. So it is in the bench wise you take out the rock. There's a huge quantity of rock which is taken out, which is then again used for port or road constructions or national highways. So what are the challenges we have faced in construction of rock caverns? This is basically crude oil caverns are 80 meters deep, and LPG caverns are almost 200-meter deep. That is the difference. Here the pressure in the caverns is maintained at 1.5 to 2 bar G, while in LPG it is 7 to 8. That's the reason why it is a difference. So this is a constructing at the 80-meter depth is a big challenge, and there you do drilling and blasting. You place the explosives in the cavern, and then you do the blast and take out the muck. So you need to have a good quality of rock. What is the depth of the overburden? What are the shear and weak zones? What is the geothermal mappings which have to done, and what is the monitoring you need to do during the construction. So this was one of the geological failures which we had during the construction at Vishakhapatnam. Like you can see at the top, wedge failures are major concern during construction and cause fatalities and can drastically slow down. So this was like the rock stone can fall during the construction period, and there is a fault line which can cause a rock slide, which is hidden behind the bench. So when the bench is excavated, what happens? Because of the weight of rock, a rock can slide and it can block. So you must have heard during the construction last year there was a in Jammu and Kashmir there was a big issue of that cavern rock fall, and many workers were trapped in that. So this comes crashing down and results in accidents and delays. Another risk is you have water ingress into the shaft. Underground aquifers are there. Water bearing zones or aquifers can result in a large ingress of water during the construction period, and then you need to pump it out continuously. So this is the actual picture of rockfall incident which was encountered during the Vishakhapatnam cavern construction. You can see almost the cavern was 98% completed, and then this incident happened, and then because of that the project was had to be again rescheduled, and it got delayed by almost 2 years. So this is a picture, like you can see how the underground water seepages are there in the work. So the workers are there working over there. So these kind of aquifers come during the construction, which we need to then again pump out the water and proceed further. Now these are the actual rocks picture which have been excavated. You can see the huge mountains of the rock, and this is actually, if you go visit any of our location, you can see at the site. And this is granite based rock. These are the mountains almost. It is there, but we are selling them for port authorities and for the construction of highways. This is a portal entrance area of a Padur site. So the large ventilation shafts which you see, it is for the air to be sent inside to the caverns where the workers are, the yellow ones, the huge ducts, ventilation ducts which you see. So these are the construction photos where you do a cavern rock bolting or face drilling. So during construction, what you need to do is you need to put on the rods by using rock bolting. So at the points where the rock or soil is loose, you need to insert the rods and do the bolting. So these are the pictures which are depicting them. And on the right side, you see the face drilling, which I told you it is a benching is done. So from top it is coming and it is going on this way. So this is the tunnel where you enter, access tunnel for taking out the material. So this is the first thing which you construct during the construction period. This is used for taking all the equipments inside, the jumbo drillings and machinery and logistics. Everything goes through this tunnel. So this is the first thing which you start during, and this goes down below till 80 meters, and from there then you start actual construction of the cavern. So this is why it is called access tunnel. So the principle of hydrogeological containment we have dealt already. So it's the same slide which he has sent. So you have a water which is maintaining those things. So this is a typical process scheme for our underground caverns. As you can see here, the top side facilities, we have a control room plus heat exchanger, pumps, boilers, then ETP. The bottom is the cavern where we have a hot oil circulation system. Above the crude oil, there is a inert gas and a water curtain. And on the left side, you see shaft, which you had seen in the picture. In that, you have a submersible pumps from crude oil and to water for taking out. The blue ones are for water, and this is connected to the SPM where you can see a crude tanker. So it is a bidirectional supply. It can we can pump out from the caverns to the tanker, and we can take from the crude tankers to the cavern. The water which is taken out is again treated in our ETP system, recirculated, and then used for horticulture, and again sent into the water curtain managements. So these are a viable alternative for crude oil storage capacities. These are perfect examples of space created without disturbing the above ground facilities. So the product is stored at a depth of 80 meters and is fully isolated. You don't need to maintain, like they are safeguarded from sabotage, storms, earthquakes, and explosions. Then this is created almost at a 50% cost of above ground facility, and with a little marginal increase in cost, you have a huge capacity enhancement. This has resulted in saving of more than 800 acres of surface land resources, which would have otherwise required to create of equivalent capacity of above ground storage tanks. Fires don't affect, and the best part is it is a sealed thing, so due to maintenance and inspection, there is no requirement, which is in case of above ground tanks, you have a corrosion, pitting, and you need a regular inspection. That kind of thing is not required. Once it is sealed, you used to them. So these are the perfect solution for effective cost storage, solution for storage. And for phase 2, we are building, as I said, around 6.5 MMT, and already the land has been acquired. Adding to this, I would like to add already MRPL and HPCL are using our caverns which are in phase 1 as an alternate for their storage tanks to refinery. So in Visakhapatnam, HPCL has already, and towards partial commercialization, ISPL has leased them to generate revenue also. So this is going to be a thing in future which we are going, and again, the innovative thing is that we are going on for public-private partnership mode in phase 2 for constructions, for which RFP is already on. So that's all from my side. Thank you very much.
Thank you. Thank you, Mr. Dashore. Necessity is the mother of all inventions, and you very well started with that. In 1970s, when there was an oil shock, we were all looking for the ways to store energy and use it for our extremely crisis purposes. So what I was thinking in your presentation, I found that you started with necessity, and the technology is a confluence of geological knowledge, construction technology, and the innate human ability to overcome the challenges. All three were there. I congratulate you for the presentation. And I was looking at this theme also, supply chain. Today I think the audience will be getting all the solutions. From storage, now the next presenter will be telling you how to transport. So may I welcome our next panelist, Mr. Dr. Yogesh Popatrao Patel, who is a Chief Manager, Petrochemicals and Polymers, HPCL, and he will be presenting or revolutionizing fluid transport through pipelines. So welcome him with a big round of applause.
Thank you, sir, for a nice introduction. As you rightly pointed out that Aftabji and Ajayji already talk about the storage of these crude oils and fuel transports. I'm going to talk about that how to transport these crude oil and petroleum products. So first, I'm very happy and privileged that I'm standing here, and thank you very much for accepting our abstract for this world's second largest India Energy Week 2025, and I would like to thank my HPCL management also that who gave me this opportunity to present. As sir rightly pointed out that research or the invention. So in the today's presentation, we are going to see that how the invention is going to the innovation, and through the innovation path that how we can success into the commercialization. So for today's talk, I'm going to talk about the drag reducing agent. This drag reducing agent generally used into the ppm level for efficient transport of these fuels from one location to another location, basically for the crude and petroleum product transportation. So I would like to talk about that HPCL pipeline operation through overall India. So HPCL is having around 5,132 kilometers of cross-country pipeline, and through this pipeline we are transporting the crude oil as well as the petroleum product. Around 3,957 kilometers of pipeline is transporting basically the petroleum products like the MS, HSDS, SKO and ATF, and 1,016 kilometer pipeline is transporting the LPG. So overall, if you see per year, HPCL pipeline around 31.11 million metric tons of crude oil and petroleum product is transporting, and around 4.1 million metric ton LPG we are transporting from one location to another location. And overall, this cross-country pipeline, if you see, we have covered most of the part of the India. Pipeline network goes from the Maharashtra, Andhra Pradesh, Telangana, Tamil Nadu, Gujarat, Rajasthan, Haryana, Delhi, Punjab, and Uttar Pradesh and Karnataka. So, to transporting this fluid from one location to another location through the pipeline, if you see overall world calculation, around 93% crude oil and petroleum product is transported through the pipeline. But to make this operation smooth, we have to add the drag reducing agent, and this drag reducing agent is nothing but these are the ultra high molecular weight based polymers that we have to add into this pipeline. So this product we have to transfer throughout the India. So our yearly requirement for the drag reducing agent is around 650 KL per year. So this is the actual genesis of the problem, that how we should make our own drag reducing agent in our own HPCL. So first I would like to give about the global demand of this drag reducing agent. If you see, the drag reducing agent market is growing with 10.2% CAGR, and it is increasing, and around 30% drag reducing agent is used for crude oil and petroleum products. This market is growing. Let's say by 2026, market will reach by $2 billion US, and if you see, there are the major manufacturers. If you see for this drag reducing agents, like they are manufacturing this drag reducing agent based on the ultra high molecular weight polymers. So first I would like to talk about what is the drag reducing agent and how this drag reducing agent works. Why we need to add this drag reducing agent into the pipeline. So first, if we understand the fundamental about the problem, then it's very easy to find the solution. So while transporting these crudes from one location to another location, this is a surface phenomena. So turbulence will create, and this turbulence will resist the flow of the material from one location to another location. And you have the booster pumps. So a lot of load will be takes place on the booster pump to transport this oil from one location to another location. So how to save the energy and how efficiently we should flow these liquid products from one location to another location, then drag reducing agent will come. So in today's presentation, we are going to see that the high molecular weight, this is the ultra high molecular weight polyalpha olefins, how help to reduce the drag reducing agent. Generally, the molecular weight of these polymers is in million, more than 10 million. And if you have more than 15 million, then your drag reduction will be very efficiently. So basically by adding this additive into the pipeline, whatever turbulence is formed, that turbulence is going to the break, and very efficiently this drag reducing agent will help to transport this fluid from one location to another location. So there are lots of challenges to produce this drag reducing agent. And basically the challenges are the type of the catalyst. Because if you want to produce this ultra high molecular weight polymer, then the catalyst should be robust. It should be robust and it should give the good conversion of the monomer into the polymer. Along with this catalysts are nothing but the Ziegler-Natta catalysts. These are the multi-site catalysts. So along with this catalyst, the donor molecule generally people are using to make this catalyst. So that donor molecule should be sufficient where this catalytic system should produce the molecular weight very high. That is one thing. After making the polymer, that the processing of the polymer, that is also one of the challenges, because the molecular weight of this polymer is very, very high. So how to process this polymer into the effective drag reducing agent, that is also one of the biggest challenge. And if you see, there are many players in the market, but this drag reducing agent, you have to add into the ppm level, but the doses of this ppm is very high. And due to this high doses, again, the cost of the material will be high. So we have identified all these challenges and we started working in our HPCL R&D center. So here I would like to take you through that how this technology we have developed into the HPGRDC R&D center. So we have developed a very novel indigenous Ziegler-Natta catalyst for this process. And one of the important component for the Ziegler-Natta catalyst that we have developed the donor molecule, which is based on a bio-based. Means one of the component to synthesize this donor molecule is coming from the biomolecule. So we made 10 different types of the novel molecules, and extensively we have evaluated all these catalysts for the polymerization reactions. More than 200 different types of the polymerization reactions we have run. We have optimized this process into the lab, into gram scale. And finally, we have scaled this polymer from gram scales to kg scale and from kg to metric ton, to the metric ton. And we found that we made more than 30 different types of the novel formulations. We have tested this formulation and we found that this formulation worked very effectively. And finally, we took the commercial trials for all these drag reducing agent. So the novel and indigenous Ziegler-Natta catalyst, as well as the bio-based donor and novel drag reducing formulation, whatever we made, that we have patented this technology in India, in Saudi Arabia, as well as Europe and USA. And we have tested extensively this drag reducing agent for 14-inch as well as 18-inch pipeline in HPCL. That is from 150 kilometers to more than 200 kilometers pipeline. We have tested our formulation, and we found that our formulation is very effective for the crude oil as well as for the finished product transportation. So we have scaled up this process and to 3 metric ton, and this drag reducing agent we have tested in our Vishaka, Vijayawada, Secunderabad pipeline, and we have optimized this process at different doses. Here we could see few data have given for representation. So around we have optimized this drag reducing agent at 3 ppm, 5 ppm as well as 8 ppm, and we got very good doses as compared to the competitors or vendor samples. So around 8 ppm we are getting around more than 41% drag reduction. At 5 ppm we are getting more than 33%, and 3 ppm That is, we are getting 23.24% drag reduction. So at itself, it is showing that whatever formulations we have developed, that formulation works very effectively for our product pipeline. And one of the breakthrough for this technology is like that the novel formulation what we develop. So it is like a complete process package from your catalyst polymerization to making the final drag reducing agent. So we have developed this complete package for this drag reducing agent for this pipeline. So we have sent samples to outside India also, to Saudi Arabia and to one of the customers, and they have tested these samples for crude oil pipeline, sir, and they found it works very effectively. So now we are closely working with those customers so that we can give this drag reducing agent in a bulk scale so that they can run in their commercial pipeline. So one thing here I would like to talk about that, as I told you rightly, that if we understand the problem, if we understand the basic mechanism about the molecules, then definitely problems can be solved. And these problems can be solved by forming a cross-functional team and utilizing the resources available in India. So I would like to highlight that this drag reducing agent, the technology what we have developed in HPCL R&D Center, is the example of Atmanirbhar Bharat, that we can make, and we can make a very efficient and sustainable solutions for our corporation, for our country. So whatever drag reduction agent we have developed, this drag reducing agent works at a very low ppm. As I told you, our formulation is so novel that it works at 3 ppm as compared to the other customers. And by using this drag reducing agent, we can save the energy. That because pump required lots of energy to pull from one location to another location, so we can save energy, and it works at a lower dosages, and it improves the flowability and efficiency of the pipeline. And one of the important parameter again, the health of the pipeline, because those who make the pipeline, they know the maintenance of the pipeline. So this drag reducing agent is a complete package for the pipeline to work for their efficiency. So with this, I would like to thank each and everyone. As I rightly told out that this is a teamwork, so that how the chemistry scientists, okay, engineers, and all pipeline people came together, and they worked together, and we got a good success for this. So thank you so much for listening me. Thank you.
Thank you so much. Thank you so much, Dr. Patil, for this wonderful presentation. And the audience would appreciate that all these presentations, the speakers are talking about unconventional products. Some years ago, nobody thought of that a rock cavern can be used for storage of oil, or rather gas also. And now, Dr. Patil told about increasing the flow rate of the same pipeline. Instead of laying another one, we can increase up to 40%. That's an unconventional way of getting things done. Now I am inviting another speaker who will be talking about an innovative product. May I request Dr. Miss Laura Crombie, if I am pronouncing it right. She is the lead chemist in Champion X, and her topic is development of a combined kinetic hydrate inhibitor and hydrogen sulfide scavenger product. Over to you.
This was quite a unique application, and when this project was discussed, initially we weren't being completely serious when we suggested the option of combining a kinetic hydrate inhibitor and an H2S scavenger. The situation was as follows. We were treating the system with KHI successfully for many, many years. The well also produced H2S, but this was treated effectively topside with very short residence time. Year on year, the H2S level was going up, and the only option was to reduce production in order to meet the specifications for the H2S level in the gas. In general, to increase the efficiency of H2S scavengers, the injection point will be moved further upstream in order to increase the residence time and to give the scavenger more time to react with the H2S. The problem was that there was no spare umbilical line available for H2S scavenger injection. So, what if we combined an H2S scavenger with a KHI? The challenge: the KHI is a polymer, while the H2S scavenger is a high pH and reactive product. When combined together, they can result in instability. The product must also be suitable for a subsea umbilical. Certain key performance indicators were set for this project in discussion with the operator. Performance of the KHI had priority over the performance of the scavenger. Blocking the pipeline with hydrates would have been a costly event in terms of production losses and remediation. Subcooling was set to 7.69 degrees C, which was based on previous KHI qualification work, which was conducted many years ago. Also, the KHI must be compatible with corrosion inhibitors. A corrosion inhibitor was to be co-injected with the KHI, but the operator wanted to replace the current product, so a number had to be tested alongside the KHI. The mass of H2S was calculated based on production data and the expected H2S level in the near future, in order to determine how much would be needed to be removed to allow the well to be fully opened. The final KPI, as already mentioned, the product had to be umbilical certified. We run stringent tests in-house to meet this standard. As the KHI component was more or less fixed, we needed to find a suitable combination of scavenger and KHI. Many scavenger chemistries are available, but ideally we wanted to stick to a similar chemistry to what was used in the field already. Initially, when products are mixed, they can appear to be compatible, but over certain periods of time, haziness, phase separation, or solid formation will be observed. Formulations which appeared to be stable were then subjected to an extended 4-week cyclic and static thermal stability test to simulate storage conditions. A pH of greater than 9 for the final formulation was the target in order to ensure effective H2S scavenger performance. Another important test was the cold centrifuge test, where the formulation was exposed to 4 degrees C for 7 days at 2000 RPM to ensure that the formulation will remain clear and no precipitation will occur. What is not listed here is that we also conducted high pressure viscosity tests to check whether there will be any changes in the product viscosity when exposed to high pressure. These final 2 tests help support the requirement for the product to be suitable for use in umbilicals. Although we knew that the KHI was working on its own, we had no idea how the scavenger and the new corrosion inhibitor would impact the performance of the KHI. On this slide on the left, you can see the hydrate equilibrium curve based on gas and water composition, with the hydrate's risk zone being on the left-hand side of the curve and being outside of the risk zone on the right-hand side of the curve. Based on system conditions, they were operating well within the risk zone at a subcooling of 7.69 degrees C. On the right, you can see the test conditions that were used to qualify the formulation in the lab. The maximum allowable injection rate was 3.5% of the product based on water due to the pump capacity. So this is where we began for the screening. Total duration of the test was 9 days, which comprised of 1 day flowing, 7 days shut-in, and 1 day restart. As the hydrate formation process is stochastic, this means we couldn't rely on just one test result. For that reason, the following setup was used to run screening tests. We call this the RC24. It has 24 blind rocking cells immersed in a water tank. Each cell has a pressure sensor attached to it, and the equipment is rated to 200 bar. Inside the cells is a stainless steel ball which provides mixing. The rocking rate is variable, and a restart shut-in scenario can be simulated. For shut-in, the tank will stop in a horizontal position. A formulation is considered a pass if 4 out of 4 cells show no signs of hydrate formation. When we tested different ratios of scavenger and KHI, we didn't know exactly how much KHI we needed in the formulation and also how much scavenger, as some information at the time was still missing. The table shows test results for 5 different ratios. and all of them pass at a dose rate of 3.5% based on water. On the right-hand side, you can see the pressure temperature profile for these tests. After we saw all these passes, we had to optimize the dose rate. But how much of the combined product do we have to apply in order to remove sufficient H2S from the system? We can calculate this. In this section, I would like to give a little bit of background as to how this calculation can be done and the pros and cons of scavenger chemistry. The chemistry which was identified to be suitable was trizene-based. Trizenes are the most widely used chemistry as H2S scavengers in the field, either by direct injection or tower applications. The main benefit is their fast reaction rates. Injected into the gas phase, they can scavenge H2S within seconds, and in the liquid phase within minutes. While they have a high capacity for removing H2S, this also comes with some limitations. As I mentioned before, the pH of the product should be greater than 9, but this increases the scaling tendency when involved in the multi-phase or even gas treatment, as this can increase the pH of the water quite significantly. For that reason, combined products with scale inhibitor and scavenger are available. In our case, a combination product was required as the product was going to be injected into the multi-phase. In general, these scavengers are thermostable up to around 150 degrees C. Reaction products such as thiazines and dithiazines, when these reaction products are thiazines and dithiazines, when these reaction products are overstressed, it means that they can react further with the H2S and solids can be formed. And last but not least, reaction products can have an impact on the crude oil quality. Operators may have to pay a fine when the concentration of reaction products are over the defined limits. The reaction between H2S and trizenes is very well known, and that we can say that 1 mole of trizene reacts with 2 moles of H2S in the ideal world, but very often there is not enough time and only thiazines are formed. Scavengers never normally achieve 100% efficiency when applied in the field. Their performance depends on many parameters such as pressure, temperature, the way these products are injected, residence time, etc. The more time available, the better performance that might be achieved. Based on this information and the molecular weight of the chemistry, we can calculate the theoretical capacity of the formulation or product. On the right-hand side, we have an example of removing 5 ppm from a gas stream for a 35% MEA trizene product. Once we knew how much H2S had to be removed, we did our calculations. The target was to remove 110 kilograms of H2S. Now we had to find the best ratio between KHI and H2S scavenger that we had tested. On a previous slide, you will have seen that we tested different ratios, numbered 1 to 5, at a dose rate of 3.5%. Here you can see the different KHI and scavenger dose rates based on the total dose rate of the product. At 3.5%, ratio 5 would only have been able to remove 105 kilograms of H2S, whereas ratio 4 would remove 158 kilograms. But for ratio 4, a dose rate of 2.5% is effective to meet the H2S target. However, we needed to determine if this ratio and this dose rate would be effective for hydrate inhibition. This slide provides an overview of all the tests that were performed. In total, we ran 168 rocking cell data points, which meant 7 tests with 24 cells. The high number of tests was required as we had to run 5 different corrosion inhibitors, as a few of them showed some impact on the KHI performance, which was expected. But in the end, a dose rate of 2.5% based on water for ratio 4 was determined, with no hydrate formation recorded during the 9-day test. An interesting fact here is that the actual KHI dose rate is now lower compared to when the KHI was injected on its own. However, this is not a surprise, as we have seen in this in the past with different KHI polymers and have previously patented these findings. So to round off the lab work we conducted, in parallel we also performed umbilical qualification tests, as we agreed with the operator that it was essential to do this, as this was the only available umbilical line, and to block this would have been a disaster. This slide gives you a rough idea of the kind of tests we needed to perform. This included the stability tests I already mentioned in one of my previous slides. High pressure viscosity tests were also performed over a pressure range up to 15,000 psi and temperature down to 4 degrees C. This also included a hold test where we kept the pressure constant for 18 hours to simulate a shut-in scenario where the product is sitting in the pipeline without movement. Full centrifuge testing was required for 7 days at 4 degrees C, and no precipitation should be observed at the tip of the centrifuge test tubes. Particle size distribution was also conducted to determine the NAS class, and also material compatibility tests were conducted. As you can see, a lot of tests were required across the various departments to bring the product to a field trial. Finally, a field trial was conducted, which was quite exciting for everyone involved in this project. We knew, or hoped, due to the reduced KHI dose rate, that the KHI would work, but would the scavenger do its job when injected into a multi-phase stream? On the left-hand side, you can see the fouling index of the wet gas line. As you can see, there are no changes in the differential pressure, and therefore the fouling index was constant. Most importantly is the graph on the right-hand side, as it shows that once the new product was injected, the H2S level went down to less than 3 ppm under full production. This product also had no impact on BS&W and OIW in produced water, so in the end, a great success. So in conclusion, a first of its kind KHI-H2S scavenger combination product was successfully developed and deployed, allowing the H2S well to be fully opened, extensively increasing the production. Increased efficiency of the combined product resulted in around $108,000 in reduced annual chemical costs and a $600,000 reduction in annual tariffs due to onshore H2S removal. The reduced H2S, of course, has led to improved HSE and personnel safety. This developed from a what-if scenario to a successful story for both parties. A novel chemical combination can be developed with the right expertise and strong collaboration between stakeholders, asking questions such as, what would you like to see and what would be the value? This project was so successful it was nominated for a World Oil Award. And with that, I would like to thank India Energy Week for allowing me to present, and thank you all for your time.
Thank you so much, Laura, for introducing a wonderful, innovative product which has been customized to a customer, but now it is being presented to all of us. And in oil industry, we know sulfur is enemy number one. We try to reduce sulfur in our products, and now any scavenger which removes sulfur H2S from the pipelines, storage tanks, actually helps in increasing the life. So thank you so much for this presentation. And now we started with storage, so we are ending with storage. So now I am requesting Mr. Puneet Gautam, who is Advisory Services Lead in Energy Arup. His topic will be demonstrating compressed air energy storage technology. Please give him a big hand.
Good afternoon, everyone, and thanks for providing this opportunity on presenting this with esteemed panel, and thanks for the chair for explaining our thing. First and foremost, I would like to explain that from where I am coming. So Arup is not a name, Arup is an organization which is based out of London, and we have a legacy of 75-year-old. We are a multidisciplinary consulting firm which is operating in starting from structural engineering to complex engineering structures, subsea cables, and entire value chain of energy life cycle. Here, I think we have heard about a lot on LPG storage and oil and gas storage in underground caverns, but I would like to bring in another persisting issues that India is facing in terms of energy storage. Yeah, thank you. So I would like to bring in another persisting issue which is related to energy storage that India is looking after, and what we are looking at is very conventional method, which is battery storage. They are producing some sort of ecological and e-waste sort of damages to our environments. So we have to explore some alternative methods which is rather conventional, and we have to look into some sort of advancement into that. So yet another that is, we need to see that how underground storage in salt caverns can be used for as an alternate energy storage, and that is rapidly, becoming a more common energy storage technologies across the globe. And there are some use cases across Germany and China that we can see that on a megawatt level some energies has been stored. So let me start with my presentation. So how it works? So it's a very simple concept of storing the energies where the natural storage the salt caravans has built, and the ambient air is being stored through compressing it by additional energy that we produce from renewable energy that we are producing. So when the demand is low, we use the energy to compress that air uh, to store it at underground levels. So it can be stored in salt caverns and as well as high pressure special purpose vessels as well. So this can be used at both the purposes. What There are three processes into that. One is the compression of the air, which is used through the electricity, and it releases some heat, which conventionally releases in the air. But when it comes to the advancement of this thing, which is another, which is called abiotic compressed air solutions. In that case, what we do, we store that heat, released heat, and we use it to reheat the stored air to increase the efficiency of the overall system. So what you are seeing on the screen as of now, it's a very schematic diagram that what we are working on as a ARUP in different part of the world as a concept and design studies, and it includes as some compression devices, and when the energy got stored and it demanded for the intermittencies of the to fulfill the FDRE or maybe RTC power supplies, what we do, we release this air and preheat it with a natural gas. So that's the conventional way. But now we are using the renewable energy to reheat it in order to increase the efficiencies of the system. So what we have seen in our use cases that if we do not reheat the air, the efficiency of the system would come somewhere around 40 to 45%. But when you heat it, the efficiency would increase from 60% to 75%. And if you use the more advancement where the slow compression is used, the efficiencies can be achieved more than 75% as well. Sorry. Now this technology is becoming the third largest after pumped storage and the BESS. So there are rapid advancement in this storage can be seen, and it's a very simple structural design, so it can be rapidly implemented as well. I would see there are some worldwide there are some projects. So overall 1.45 gigawatt of compressed air installations has been done. So there are one project of 290 megawatt in China is already commissioned in January of 2025, and another project which is on the conventional side of this is operating in Germany. And there is another project which is under construction that is in McIntosh in USA. So now where we are going to need it, where the renewable energy is being used as the intermittent power supply. So we need to fill that gap and to use for the hydrogen production. So co-location of these technologies when we use as a high pressure can be, would be more useful and fruitful for going forward when we look into the more advancement into an energy storage system. There are certain advantages and disadvantages of these technologies, but I see advantages as a more prominent thing, and which comes as it has a rapid startup time. Mechanical system is very simple, which everybody is using when we generate from the gas turbines. They have longer asset life, so when you compare it with the battery storage system, which is easy to implement, but rather comes up with a lot of hurdles in terms of impacting your environment. So it has an asset life as well as compared to as pumped hydro storage. So they can be used as a complementary storage solutions. Efficiencies, as I told you, there are different methods to increase the efficiencies more than 75%. Then that's what industry is looking as of now. there are continuous improvements in the developments in the field like abiotic and supercritical, where we introduce CO2 in order to store as a fuel, and where hydrogen storage can be utilized. I think there is less biodiversity and ecological damages in comparison with the batteries and the other systems. And even on the pumped hydro side, if you'll see, there is a huge ecological damage we have seen in the past. It's a fair comparison that on the screen that I'm showing you as of now, that what we have seen here, that battery storage systems are easier to implement, and pumped hydro systems required a longer time to implement on the similar scale. But when you put compressed air energy storage in middle, I think it can serve as a middleman where we can utilize each nook and corner of energy storage systems. So it can be used as a moderate energy storage systems. This is we have mapped some sort of where are the natural voids can be found in India, and that can be explored. So the places like Gujarat, Madhya Pradesh, and Uttar Pradesh in the map, which has been highlighted in the red, can be explored as a further exploration for these sort of arrangements. And there are some when I talk about policies and the regulatory aspect, I think in the hydrogen mission, also government is also providing subsidies on these sort of storage systems, so that they are also can be leveraged in the longer run. As a Arup, we are doing a lot of projects globally in terms of energy storage system, which includes Electric CES's 268 megawatt Northern Ireland project, where we have done the concept designing of these storage tanks, and we have built a special purpose high pressure storage tank to store the energy, and it's in the concept design stage, and we are working as a owner's engineering for that one. We have worked for such gigafactories in the storage system, such as Tesla gigafactories as well. So this is our capabilities in those things, and we are working on some sort of hybrid systems as well on providing some sort of hydrogen to make the entire system green, rather than depending on the natural gases, which has been utilized on the natural gas side. So this is from the Gala Electric Energy Storage. So this is the services from the program management and the electrical engineering side we have supported, and we have a very nice geotechnical team who has explored these sort of engineering marvels as and when required. So this is something a live example that our team is working on. So this is something that I wanted to present in front of this esteemed group of experts, and this is all from my side. Thanks a lot for hearing me, and have a good conference. Thanks, everyone. Have a good day.
Thank you so much, Puneet, for giving this presentation on energy storage. What a wonderful session it was. All the speakers, they have given us unconventional methods of storing energy, transporting it, and innovative products, how to keep our assets intact. So, and special thanks to you for making it in time. So I think we are well within our time. I can request audience, my special thank to audience that they have been here patiently listening. If there are any questions, we have 2 minutes. We can take up 1 or 2 questions. If no questions, so I expect that this session was well understood. So a wonderful session, and thanks to all the audience for being patient and patiently listening to us. Thank you so much.